We've all seen those incredible videos, right? Humanoid robots walking, running, even doing backflips. And the AI brain seems to get all the credit. But today we're going to pull back the skin, look past the hype, and get into what it really takes to build the body of these amazing machines. All right, let's get into it.
So this is the big question. How in the world do you get a two-legged machine to walk? It sounds so simple, but believe me, getting a robot to move and balance like a person, that's one of the toughest puzzles in all of engineering. It's this incredible dance between raw power, pinpoint precision, and constant, non-stop correction.
You see, it's easy to assume it's all just about a super smart AI. And look, that software is a massive piece of the puzzle, no doubt, but it is not the whole story. Because the smartest brain on the planet is completely useless if it doesn't have a body that can actually listen and move effectively.
Yep, that's it. The real secret sauce is in the hardware. We're talking about the motors, the wiring, the communication network, the physical body that has to take every single command from the brain and execute it with flawless precision. So today, that's what we're going to do. We're going to build that body, piece by piece.
Okay, first things first. Every robot body needs muscle. And in the world of robotics, we call these things actuators. The absolute workhorse for any humanoid is something called a servo motor. But let's be clear, this is not the simple little motor you'd find in a kid's toy car. Oh no, it's way more sophisticated.
The two words you have to burn into your brain here are closed loop. See, a servo motor isn't just one thing. It's a whole system packed into one unit. You've got the motor itself for the power, a gearbox to multiply the torque, a sensor to provide feedback, and a little control circuit that acts like a local manager. It's basically a self-contained, intelligent muscle.
And how it works is it's brilliant. The main robot brain sends a command, something like, hey, move the hip joint to exactly 35 degrees. Instantly, the servo's internal sensor checks, okay, where is the hip right now? If it's at, say, 34 degrees, it calculates that 1 degree difference. That's the error. Then the drive kicks in with just enough power to fix that tiny error. And this whole loop, command, compare, correct, it happens hundreds, sometimes thousands of times a second, constantly.
So you might be thinking, why not just use a simpler motor, like a stepper motor? Well, here's the deal. A stepper motor is kind of dumb. If you push on it and it misses a step, the robot's main brain has absolutely no idea. It thinks its foot is in one place, but it's actually in another. And that, my friends, is a recipe for a faceplant. A servo motor, on the other hand, is smart. It feels that push, knows it's off target, and actively fights back to hold its position. When it comes to balance, that's not just a nice feature, it's absolutely essential.
All right, so we've got our smart muscles. Awesome. But how do we actually assemble them into a working leg or an arm? Well, this brings us to a huge fork in the road for any robotics engineer. It's a central trade-off, really, with two very different philosophies on how to build a limb.
So the old school way is what's called the discrete approach. This is where you buy the motor, the drive, the sensor, all as separate pieces, and you have to wire every single one of them together. Now, for a humanoid robot with maybe 40 or more joints, this creates what one source so perfectly called a veritable rat's nest of hundreds of individual wires. It is a complete nightmare. It's heavy, it's messy, and it's just begging for something to break.
Now, contrast that with the modern solution, the integrated smart servo. In this approach, all those components we talked about, the motor, sensor, gearbox, controller, they're all pre-packaged into one single clean module. And the best part? You connect them with a simple daisy chain. One cable runs from the hip to the knee to the ankle. All that complexity we just saw, it just vanishes.
So this table really lays out that big trade-off. On one side, the discrete approach gives you maximum flexibility. You can mix and match parts to get the absolute peak performance for every single joint. But the time and complexity, it's just huge. On the other side, the integrated smart servo isn't quite as flexible. But because it's basically plug and play, your development speed is off the charts. You can build and scale a robot so much faster. And for most teams out there, that speed is the game changer. Okay, we've got the muscles, we've got the limbs, now we need the nervous system.
This is the communication network that lets the brain actually talk to the body. And let me tell you, this is just as critical as the actuators themselves.
For a long time, the standard way to do this, and what a lot of hobbyists still use, is something called PWM, or pulse width modulation. It's basically an old-school analog signal. You send an electrical pulse, a short pulse tells the servo go to 0 degrees, and a longer pulse tells it go to 180. It's simple, for sure, but for what we're trying to do, it's deeply, deeply flawed.
And here's exactly why PWM is a complete non-starter for a complex humanoid. First, it's one-way communication. The brain can shout orders, but the muscles can't talk back. You get no feedback on what's actually happening. Is the joint in the right place? Is it overheating? You have no idea. Plus, you need a separate wire for every single joint, which brings us right back to that rat's nest we worked so hard to get rid of. It just doesn't scale.
This is where modern digital communication buses come in and save the day. Two of the big ones you'll hear about are CAN bus and EtherCAT. CAN bus is a total workhorse. It's incredibly robust. Its killer feature is message priority, which means a critical message like, "Whoa, I'm falling," will always get through the network first. Then you have EtherCAT. EtherCAT is the absolute gold standard when what you need is perfect synchronization and speed across every joint in the entire robot.
So, EtherCAT's secret sauce is this incredible idea called processing on the fly. Here's how it works. Instead of sending a separate message to each joint, the master controller sends out one single data packet, like a train. This train flies through every single servo on the line without stopping. As it passes, each servo snatches its own orders off the train and, in the same instant, puts its own feedback data back onto the train. This whole round trip happens in nanoseconds. The result? Every single joint on the robot is perfectly synchronized, down to less than a microsecond. This is how you get that smooth, stable, coordinated walking motion.
So, where are we headed from here? You might think all the action is in the AI, but this hardware, the body, is evolving just as quickly. Let's take a look at the big trends that are shaping the future of robot bodies.
First off, let's just follow the money. Take a look at this. The actuators, the muscles, they can make up almost half the entire cost of a humanoid robot. That's a huge number. And because of that, there's this intense pressure and innovation to make them cheaper, more powerful, and more efficient. That drive is what's eventually going to make these robots affordable for everyone.
Now this is a question I hear all the time. If wires are such a pain in the neck, why don't we just get rid of them? Go completely wireless?
And, it's a great question, but the answer is a little complicated. For stuff at the end of the arm, like a gripper or a drill, wireless is fantastic. It gets rid of cables that are constantly flexing and breaking. But for the main joints, the hips, the knees, the torso, absolutely not. There's just no way to wirelessly deliver the hundreds of watts of raw power those joints need to hold the robot up. And even more importantly, you can't guarantee that rock-solid, microsecond reliability you need to keep it from falling over. So for now, the core of the robot is staying wired.
And this really brings us to the biggest change in thinking of all. The actuator is fundamentally evolving. It's not just a motor anymore. It is becoming a full-blown networked IT device. Think about it. It has its own processor, its own network address, its own security protocols, its own ability to report diagnostic data. We're not just wiring up motors anymore. We're managing a fleet of intelligent computers distributed throughout the robot's body.
All right, let's bring it all home. Let's put everything we've talked about together. If you are building a humanoid robot today, what's the blueprint? What are the key takeaways?
Here's the modern blueprint. It starts with the muscle. You've got to choose a smart, closed-loop servo motor for that reliable control. Next is the architecture. You have to make that critical choice between the ultimate flexibility of discrete parts or the incredible development speed you get from integrated servos. Then, for the nerves, you have to pick a modern digital bus like CAN or EtherCAT that can deliver the performance and synchronization you need. And finally, the future. You have to start thinking of these actuators not just as hardware, but as intelligent, networked IT devices.
And that really leads us to one last big thought. As every single component in the robot gets smarter, gets more connected, it forces us to ask a really fascinating new question. At what point are we no longer just building a machine,
At what point are we actually deploying a distributed IT network that just happens to be shaped like a person? That blurring of lines between mechanics and information technology, that's the next great frontier in robotics. Thanks for joining us for this Explain.